New pictures obtained by the James Webb Space Telescope have stunned researchers. Instead of expanding our perception of the universe, these pictures revealed a disturbing reality: our current understanding is insufficient to grasp the nature of the universe in its earliest stages. The hypothesis of the universe's origin seems to reach its limits, prompting us to consider new theories about its beginnings. The question arises: how was the universe formed comprehensively, and why? This new revelation challenges even the most experienced space specialists to uncover more about the Big Bang and the ever-evolving nuances of discovery. We must reassess the validity of the Big Bang itself. Contrary to popular belief, the Big Bang was not an explosion in pre-existing space. Rather, space itself began expanding approximately 13.8 billion years ago alongside matter and time from a singularity, a point where gravity is so intense that the curvature of spacetime becomes infinite. Today, billions of years after the universe's formation, we see that our celestial home is part of a vast cosmic structure. For experts, this represents a crucial aspect of the universe, since its very existence and continuous expansion are key to understanding its nature. The universe is not expanding into pre-existing space. Rather, space itself is continuously growing. According to conventional theories, the first stars began to shine between 200 and 300 million years after the Big Bang, marking the end of the so-called Dark Age. This was when the first luminous celestial objects clustered together to form mature galaxies. However, how quickly these galaxies developed remains an ongoing mystery. A significant discovery emerged with the first images captured by the James Webb Space Telescope in July 2022. Experts announced that the telescope had detected various galaxies, some of which existed around 300 million years after the universe's formation. However, compared to celestial structures that formed billions of years later, these early galaxies were considerably smaller and less massive. This finding aligned with the accepted scientific model, which suggests that the density of matter in the young universe was too low to form galaxies as large as those observed today. Then came an astonishing revelation: the discovery of 6 unexpectedly massive redshifted light sources detected by Webb, triggering one of the most significant astronomical crises in recent times. Although these newly discovered galaxies were similar in age to previously recorded ones, they were nearly as massive as our own Milky Way. This has created an intriguing mystery in cosmology. After examining a series of images captured by Webb's near-infrared camera, experts identified these light sources using redshift measurements. Specialists confirmed that the light from these objects took over 1 billion years to reach Earth, meaning they existed between 570 and 700 million years after the Big Bang. Analyzing their properties, researchers concluded that Webb had captured 6 early galaxies in the images. Shockingly, these galaxies were so massive that they defied conventional cosmological assumptions. Instead of the expected, dwarf galaxy structures were identified that were almost as large as the Milky Way, despite having formed so early in cosmic history. If we continue analyzing Webb's data, we find that these gravitationally bound collections of stars already had masses exceeding 10 billion times that of the Sun at the time, with one possibly reaching an astonishing 100 billion solar masses. Even in this scenario, the mystery remains unresolved. If these galaxies truly existed as observed, the early universe must have contained much more mass than previously estimated, presenting a fundamental challenge to conventional cosmological models. Even if only one of these galaxies is confirmed, it would force scientists to rethink our understanding of cosmic evolution. The density of matter in the early universe would have to be several times greater than accepted theories predict. Another equally baffling possibility is that these galaxies formed through processes completely unknown to us. These discoveries, along with the debates they have sparked, are leading to renewed scrutiny of the Big Bang theory. Many astrophysicists with alternative views express frustration as their perspectives are often overlooked in mainstream scientific discourse. Even experts who uphold the Big Bang theory continually face unanswered questions. One fundamental inquiry concerns how 13.8 billion years ago something seemingly emerged from nothing. Could the universe truly arise from nothing, or was there a triggering event? Was it a random occurrence? Stephen Hawking argued that time itself began with the Big Bang, meaning the process could not have been initiated by anything external. Another puzzling question relates to the uniformity of radiation and matter distribution throughout the universe. Regardless of where or how far we look, the large-scale structure appears remarkably homogeneous. Modern theorists explain this through the theory of cosmic inflation, which suggests that a rapid expansion in the universe's infancy smoothed out irregularities. However, some experts extend this idea further with the theory of eternal inflation. This proposes that inflation continues indefinitely in some regions, forming multiple universes, each with its own distinct physical laws. This raises a profound question. What if our universe is not the totality of existence? More provocatively, what if another universe preceded our own? In this scenario, the Big Bang could be part of a recurring cycle. Some models suggest an eternal pattern of cosmic collapse and rebirth, where the universe undergoes continuous cycles of expansion and contraction. Alternative cosmological theories challenge the standard view of the universe's origin. In 1955, for instance, a paper suggested that the universe may have always existed without a definitive beginning. According to this hypothesis, the universe is not expanding. Rather, new matter continuously forms, creating the illusion of expansion. A more radical theory emerges from quantum physics and string theory. Some experiments suggest that our universe may be a projection, a higher dimensional simulation. While this might seem like science fiction, it aligns with the Kardashev scale, which classifies civilizations based on their ability to harness energy. A Type 3 civilization capable of utilizing the energy of an entire galaxy could theoretically create a perfect simulation. However, proving such a scenario is an extraordinarily complex challenge. The mysteries of cosmology and the origins of the universe continue to push the boundaries of human understanding. The James Webb Space Telescope's discoveries have reignited discussions about the very nature of reality, challenging established theories and prompting scientists to reconsider fundamental aspects of cosmology. At the heart of this inquiry lies the question of how the universe began. The prevailing model suggests that around 13.8 billion years ago, the universe emerged from an incredibly dense and hot state, expanding rapidly into the spacetime and matter we observe today. This was not merely an explosion, but rather the very birth of space itself. The notion of a singularity where spacetime curvature becomes infinite remains a cornerstone of this theory. Yet Webb's discoveries challenge our assumptions about how quickly galaxies formed. The existence of such massive galaxies so soon after the Big Bang suggests a much greater density of matter than previously estimated. This deepens the mystery of how these structures could form so rapidly. Moreover, these findings raise fundamental questions about dark matter and dark energy, two mysterious components that comprise most of the universe's mass-energy content. While dark matter is thought to provide the gravitational framework for galaxy formation, its role in the early universe remains unclear. Beyond astrophysics, some theoretical physicists explore alternative cosmological models, including the possibility of a vast multiverse. Some theories suggest that inflationary expansion never stopped in certain regions, continuously spawning new universes with unique physical laws. One particularly bold idea is that our universe exists within a simulated reality akin to a highly sophisticated computer-generated environment. This notion, inspired by advancements in artificial intelligence and computational science, raises profound philosophical and scientific questions about the nature of existence itself. Advancements in observational astronomy, such as those provided by Webb, will continue to reveal the universe's deepest secrets. Future observations may shed light on the earliest moments of cosmic history, helping us unravel the fundamental principles that govern its evolution. Meanwhile, the search for extraterrestrial life remains a key focus of scientific exploration. The discovery of exoplanets has expanded our understanding of potentially habitable worlds, and future missions may detect biosignatures indicating life beyond Earth. As we probe the universe's origins, cultural and philosophical reflections also play a role in shaping our understanding of our place in the cosmos. Questions about existence, intelligent life, and humanity's future in space continue to drive research and debate across scientific disciplines.